Thank you. All right, welcome back. First, I want to amend this last slide. As people noted, there was a slight issue in my eagerness of making for a nice compact statement. I removed the existence part, which is pretty important. So if you have a Grobner basis, if and only if any polynomial in the ideal generated by the Grobner basis can be written this way for some q's, so that this maximum property is satisfied. You don't get to pick the q's, they exist. If you take a generating set that's not a Grobner basis, then those q's that satisfy this might not exist at all. That's the point. So hopefully that's better. And there should be a new version of the material with some typos corrected here and there. So thank you for all who contributed. Now I want that to go away. Fast forward to day 2. Welcome to day 2. You had a whole day to learn all about computing Grobner basis. And I actually would like to first just say something technical but useful. So I don't know if you had a chance to actually get to those problems that ask you to compute Grobner basis by hand. Maybe some have, maybe some haven't. Maybe you can try later. And maybe some of you have already played around with software that can compute Grobner basis. And chances are that if you compute it by hand and then you use the software, or maybe if people computed separately and then compared results, they might have gotten different things. And that is okay, because if you have a Grobner basis of an ideal, then you can just throw more stuff from the ideal into that set and it still remains a Grobner basis. All right. Typically, in fact, you want to remove stuff, but still obtain a Grobner basis. And if you do that enough, you actually get to something unique. So if we all agree to certain rules, namely that we want the elements in our Grobner basis to all have leading coefficient 1, and we want it so that no monomial of any of the elements in this tuple, any element little g in this tuple, is divisible by the leading term of the other elements of the tuple, then you actually get something that is called a reduced Grobner basis. And in fact, a theorem says that once you have fixed your monomial ordering, then every non-zero ideal has a unique reduced Grobner basis. Okay? I want to point out that this is helpful because if you remember, one of the motivation questions from this morning was actually ideal equality. How do you test two ideals are equal? Well, okay, if you have I and j and you have generating set for 1, you can start from there and compute a Grobner basis. Then you can start from j and compute a Grobner basis, and now you can check if the elements on one side belong in the other ideal by doing a lot of divisions and checking remainders are 0. Or, better option now is compute the reduced Grobner basis. The ideals are going to be the same if and only if you get exactly the same thing. Okay? So in fact, for example, software would probably do this to check two ideals are equal. I also want to point out that this gives you some nice little corollaries. I guess I mentioned the first one already. Yes. And then, of course, if the ideal are equal, the equality doesn't depend on the Grobner basis. So if the Grobner basis is equal in one ordering, it will be equal in the other, in any other order. But another interesting one was, I don't think I stated this explicitly this morning, but you may have a set of polynomials and look for the vanishing locus in affine space, the set of all common zeros of those polynomials. An interesting, more basic question is, does it actually contain any points, or is it empty? And well, we can write this down. So if you give me an ideal, and we're going to work over a field with that is algebraically closed, then the vanishing locus of the ideal is empty if and only if the reduced Grobner basis of the ideal contains 1, or is equal to just a tuple containing 1. If you're not looking at the reduced Grobner basis, you could say a Grobner basis contains a constant, a non-zero constant, and that would be equivalent to this statement. One direction going from, well, right to left, I guess, is easy, and that's the Grobner basis stuff. The other one is not trivial. You might have heard of the Null-Stellensatz theorem, so there's more going on here. But maybe the new part, if you haven't seen it before, is the Grobner basis side of things. Right, so sometimes this is called consistency, if your system of polynomial equations even has a solution or not. I also want to point out one thing here. For the theoretical result, you need the computation over, well, you need to work over a field that is algebraically closed. But if you think about the polynomials that we worked with this morning, right? The coefficients could have just been rational numbers, and then we have seen how to construct a Grobner basis. All the computations involved are just linear combinations of polynomials. And so if you start with coefficients in Q, your Grobner basis will end up also with coefficients in Q, right? So even though for this result, to take away the fact that the vanishing local is mean 0, you need the algebraically closed field, but for the computation, you do not. Okay. All right. So now for the rest of this talk, I want to give you a couple of simple applications of Grobner basis. And then let me also say at this point that if you get a chance to look at the problems for day 2, so halfway through the notes, I think I make a suggestion that people do one of them in particular if they haven't seen it before, again, because that will set up a nice example for the problems in day 3. And that will be, it's called problem 21. But then most of the other problems, you should think of this set of problems for day 2 as being like a showcase of applications, expo day for Grobner basis, right? So if you're looking at doing some of those problems, I would just say just scan through, read through, and pick 1 or 2 that you might like, and there's different applications. So I leave it up to you to figure things out. All right, so how can you use Grobner basis to solve systems of polynomial equations? So I have this picture over here, and maybe the colors didn't come out so well, but that's okay. We have a sphere, we have a plane, and we have a hyperboloid, I guess. And they're lined up nicely. They meet at 4 points, 2 here and 2 at the back. They might be harder to see. But all of those surfaces can be represented by polynomial equations. So if we solve the system containing all those equations, we should figure out what those points are. And so that's the system of equations for those surfaces. Let me point out, this is in a way a little bit of a silly example. The last equation, x equal y, means you can get rid of a variable to begin with, right? So, okay, but I wanted something that also gave a nice picture, so I decided to go with a plane. All right, so let's pretend we haven't noticed that. Let's use all 3 variables. And let me show you how to do this with Grobner basis. So I have some code here for Macaulay 2, and I want to, this is not a Macaulay 2 workshop, but I also want to take the opportunity to advertise this software for some computations. So if my things here are done properly, I should be able to copy this. And then I'm going to go to my browser. There's Macaulay 2, macaulay2.com. And you can download the software and try to install it on your computer. If you're just trying a quick computation, what you might do is go here where it says on the left, try it out, Macaulay 2 Web. And I already have that in another tab. You may need to start it if you get here at first, but then it will give you a terminal on the right running Macaulay 2. That's where we're gonna see the result. It also gives you an editor on the left. You can just put text in there. I don't really use this most of the time, but I think if I press that, yeah, I should clear it out and I can copy my code in here. And if you want to write comments in your code, you can put 2 dashes. So this is solving, whoops, equations. Okay. So let me go line by line. So when you have your cursor on a certain line, if you haven't, is this big enough to see? I should probably make it a little bit bigger. Is that okay? People at the back, or maybe a little more? If I make it too big, then you won't be able to see, but I can also make it smaller later. Okay, all right. So don't worry about on the left, you're gonna see it on the right. So my cursor is on the second line, r equals something. I'm gonna press the play button, it's gonna send it in there. So now Macaulay 2 has created an object of type polynomial ring, QQ for rational coefficients, variables x, y, z. The default order is G rev lex, graded reverse lexicographic order. If you want something else, you have to specify it, and this is how you do it. Monomial order gets lex. I want to use the lexicographic order, and we're gonna see in a moment why. So then I have my next line, which defines the ideal with the generators corresponding to the equations that I have in my system. I just want to point out that this was an issue, not an intentional trick on my part for some of the problems from the morning session, that I tend to write polynomials with the monomials with larger degree first, but if you're using lex, you know By now, that's not always the case. But however you put your polynomials in here, even if you have some algebra that's not expanded, Macaulay 2 will expand all of that stuff for you. Actually, I don't have it in there, but I can show you. If you already have the ideal here and you want to see the generators, you can do I underscore star. And if you want, I think this should print nicely if I do this. Let me try it. Well, nicely, relatively, but at least you can see them. It's not tech. The previous line was tech. All right. So anyways, we have the idea. We have fixed the monomial ordering. I'm going to ask Macaulay 2 to compute a Gröner basis. I should say maybe there are different ways to do this, but GB is a command. GB of I will return an object Gröner basis of the ideal I, but it doesn't tell you what that looks like. Essentially sets up the computation, and the way because it's done this way so that you can actually tweak this computation. Maybe you don't actually want it to start yet, you only want to go up to a certain number of steps in the algorithm, so it's set up that way. If you actually want to see what that Gröner basis looks like, you want to do gens of G, and that is my Gröner basis. Okay, so maybe now I can actually use the board. Is this good enough earlier? Sure. So I was told that I can actually use the boards. The problem is that in the recording of this, people will not be able to see the boards because they will only see this and they will see a tiny little window with the boards. So, all right, well. Okay, so here we have our Gröner basis. So how should I think of this? This is a different set of generators for the same ideal. So if I'm trying to solve the original system of equations, I might as well solve this one. We're going to get the same solutions, right? But you might see already that there's something useful in there. You have this equation that only contains one variable, right? And so that should be 0 or 1. Okay? Now, before I go further, let me point out that it came out this way because we chose to use the lexicographic ordering. Okay? So any polynomial that has a leading term that's a power of z will be relatively small in the lexicographic ordering, right? In fact, all the terms that come after that will also be only powers of z. Okay, and this is why we made this choice over here. So if you can single out an equation in one variable, then that's some good progress. Of course, we can plug the z in here. So when z is equal to 0, we'll get 2y squared is equal to 1. Am I doing this right? And so y should be plus or minus 1 over the square root of 2. And then the x and the y are equal. This is what the last equation tells me. Yes? Yes, exactly. So it's going by the smallest of the leading terms. Right? Actually, I should also have said that when you do this, Macaulay 2 will always return the reduced Gröner basis. So the leading terms are going to be different, so they can be ordered, but with a caveat. Remember, I said all the leading coefficients should be equal to 1. And you see this over here, that's not a 1. I think this was a deliberate choice on the part of the authors, because otherwise, to have a 1 here, you need to have denominators. And denominators don't look as nice. So I think they made a deliberate choice, which I'm happy with. I'm okay with that. Okay, and then x is equal to y. That's the last equation. So you get z equals 0, x and y equal, you get these choices over here. Or if z is equal to 1, then what do we get? 2y squared is equal to 2. And so y is equal to plus or minus 1, and same for the x. Okay, so not the best organization, but I hope you can see where this is going. We can get all the solutions this way. So a word of caution, you probably don't want to solve arbitrary systems of polynomial equations this way. First of all, I'm not entirely, I don't think it's a guarantee that you're always going to come up with something like that. Actually, for this example, you could even use the default order, and I think that equation will pop up, I believe. So you may not need to use lex. And the lexicographic order typically tends to give very big Gröner basis if you have a lot of variables, lots of generators, so it may not be the most efficient choice. So if you're still just looking to solve the system of polynomial equations, you're probably better off doing it numerically. But anyways, this is something you can also try. Yeah, is that good enough? Any questions? So I forget, we started at 420, so that means 450-ish. Okay, perfect. So let me go back here. Now I have to restart this thing. Okay, so we did this, right? We solved the equivalent system given by the Grunberg basis, so we're done. All right. Here's another interesting application that I want to talk about, elimination. This is a big one. You'll see a lot of the problems for day 2 are based on the ideas that I'm going to talk about here. So in this example, I have a sphere in 3-dimensional space, and I want to construct a parametrization of the sphere, which you probably have seen before. This is sometimes referred to as stereographic projection. You pick the North Pole, and you look at all the lines passing through the North Pole. They will hit the sphere at some point, and they will also hit your xy plane at another point. So you can use the 2 coordinates of the point in the xy plane to give you parameters, and for each one of these, you get a point on the sphere. Okay? All right, so you can write that parametrization down. It's a rational parametrization of the sphere, and it looks like that. And so whenever you have parameterizations, think about problems in Calc 1, right? If you want an implicit equation, you want to eliminate the parameter. And so that's something we can also do with Macaulay 2. I wrote some code here, so let me play this game again. I'm going to copy it. I'm going to switch back, and I'm going to put it in my editor over here. So here I'm going to say elimination. Actually, what I'm going to do is I'm going to restart. So I want to clear any existing variables. So restart will do that for you. And now I'm going to start sending stuff over to the right. And let me explain as I go along. So here, what do I have? I'm not going to bother making this a slide again. I need all the variables that appear. This is a little bit tiny, but I have x, y, z, and then I have the 2 parameters u and v. Okay, so I want all those variables, but remember, eventually I want to eliminate u and v. And also, because I see better here than in the code, I have denominators, and that gives me rational functions. I want to work with polynomials. So I'm going to clear denominators and put everything on the left. Fortunately, it's the same one. It's 1 plus u squared plus v squared. So I'm just going to multiply all those by that and form polynomial equations that way. So yeah, let me also put in the ideal. So the ideal will be generated by those equations from the parameterization after you have eliminated the denominator. Now, when I set up the ring, I told my colleague to start with u and v, then x, y, z, and then do an elimination order. So this morning, I suggested that you try your hand at problem 4, which really just became the last bullet point, the third bullet point of problem 4 for technical reasons. But if you have seen that, then you know now that there are some monomial orders that are called elimination orders, or they depend on certain weights. And in particular, the one that you would use here, I guess, is the one that gives weight to these 2 things. And then the rest comes later. And the advantage of that is that you can basically, what did we say the definition was for that? I think anything that has a u or a v variable is bigger than anything that has only x, y, and z variables, right? And so it kind of plays a similar game to what we have seen with the lexicographic order before, but these monomial orderings tend to be a lot more efficient than lex. So that's why you should probably use these going forward instead of lex. Eliminate 2 is because I want to eliminate the first 2 variables. All right, so let me proceed then. I'm going to do the same thing as before. I'm going to have Macaulay to compute the Grunberg basis. It tells me it's there, it's done. It doesn't show it, but I can have it print that for me. And maybe I can show you the whole thing. Well, oh, it's 6 terms. 1, 2, 3, 4, 5, 6. Okay, that should be it. All right, so that's the whole thing. But remember, we want to get rid of u and v. So we only want to look at the specific part of this Grobner basis that has the variables x, y, and z. Unfortunately, if you only care about that, you can read it off. It's just the first entry, right? Okay. But if you actually need to access that, maybe you might do something like this. There's a command, select in subring 1 gens G. So let me walk you through that. Gens G is this 1/6 matrix that we saw before, right? And then when we constructed the ring with this particular monomial ordering, secretly Macaulay 2 created blocks of variables. The first block is the one containing the two that we want to eliminate, u and v, and then there's a second block containing x, y, and z. When you say select in subring 1, it means remove stuff that lives in the first block. So remove u and v. So only select the stuff in this matrix that does not contain u and v, and that returns only this one equation. Okay. Of course, it is the equation that you know and love for the sphere. So probably this result is not very surprising, but this is one way to prove that. Okay. Any question? Let me point out another thing. This is going back to the picture of the stereographic projection. That kind of parametrization covers the entire sphere except the North Pole, right? We chose to have lines going through the North Pole, so we don't get something that parameterizes that point. And that's okay, but when we're doing algebraic geometry, we want the loci of polynomial equations need to be closed in the Zariski topology. So this equation also contains the North Pole, right? So really, if you're missing some points from the parameterization, this will pick them up. Okay, so I actually don't think I have a lot more, but I did want to finish with sort of I know it's the end of it, but I want to make this discussion of the elimination just a little bit more precise with some definitions. So, all right, we have an ideal I in this polynomial ring with n variables. We're going to define the mth elimination ideal that we denote I sub m as the ideal in the subring containing the variables towards the end. We eliminated the first m, and it is obtained by intersection. Okay, so it's an ideal in a subring, and then a monomial ordering on kx1 xn is of m elimination type if every monomial involving one of the first n variable is greater than all the monomials that only involve the later variables. Okay, so the elimination order, the weight order that you might have seen in problem 4, that's one of those, right? I guess the lexicographic ordering would also be one of those, but for other reasons, not necessarily your best choice there. And I actually think this is my final slide, so maybe this went a little bit fast. But all right, this is the main theorem behind what I've shown you for elimination. So if you start with an ideal in your polynomial ring and you compute a Grobner basis with respect to a monomial ordering of m elimination type, when you take the polynomials of that Grobner basis that only use the later variables, you get a Grobner basis of the mth elimination ideal. Okay, and this is important in a number of ways. When you are removing variables, geometrically corresponds to removing coordinates. So it's like doing a projection from a bigger space to a smaller space. So this is sort of the algebraic version of that. This is sort of a, well, yeah, I guess you say this is sort of first step in many other computations that you might want to do. So some of the problems toward the end of the list here for day 2 are just slightly more theoretical. For example, how, if you haven't seen this before, how do you compute the intersection of two ideals, right? You can do it with Grobner basis, but then you use an elimination. And there's also colon ideals that we've seen in other talks as well. How do you compute colon ideals using Grobner basis? You can do that, but they require intersection, which in turn you can do with elimination. So elimination really underpins a lot of the computations that are done with Grobner basis, and you'll see in many of the problems. So that's it. I'm going to stop here.